So, we talked about PN junction diode and its application as a rectifier. There are some special purpose PN junctions like LED or photodetectors or the solar panel. So, I will be talking about these, but before that let me do some numerical problems to give more familiarity with this semiconductors and PN junctions. So, today we will do some numericals. The first one is that if you have a semiconductor and allow light to fall, monochromatic light, then how much of it is absorbed and how much it is transmitted. So, the problem says that a monochromatic light is made to fall on a semiconductor, and it is found that if lambda is less than 817 nanometers, so if wavelength is less than 870 nanometers, the semiconductor is opaque. Semiconductor is opaque, but if lambda is more than this, this becomes transparent. So, if lambda is more than 870 nanometers, then it becomes transparent. That means the absorption is very small. And the question is, what is the band gap? Right? So, you have a semiconductor and you allow this light to fall on this semiconductor. It is a monochromatic light, and you change your light source and work with different wavelengths. And you find that if wavelength is less than 870 nanometers, then there is a lot of absorption. It is opaque, the light is not coming out. But when lambda is more than 870 nanometers, then a lot of light is coming out, the absorption is very small, and it looks like as if it is transparent. And then what is the band gap? So, what is the relation of this absorption and the band gap? You have the semiconductor, so you have a valence band, you have conduction band, and then there is a band gap, Eg. So, if light falls on this, light photons have certain energy, and you can calculate what is the energy of the photon corresponding to this particular wavelength. So, if you calculate that energy of the photon, of 870 nanometer light, that energy you can calculate, it is hc over lambda, and this is Planck's constant, and this is the speed of light. You can multiply them, and that turns out to be almost 1240 eV nm, and this lambda is 870 nm. So, you can work out how much is this energy. So, 1240 divided by 870. So, let me calculate. This is 124 and divided by 87. So, divided by 87, and this is 1.42, almost 1.42 eV. So, that means if lambda is less than this, that means the energy is more than 1.42. So if energy is more than 1.42, then it gets absorbed. It is opaque, light doesn't come out. So absorb means what, and how can it absorb? It can absorb if the band gap is 1.42. Then this photon 1.42 eV can get absorbed and can take an electron. This is valence band and this is conduction. It can take an electron from this valence band to this conduction band, right? And if the wavelength is still smaller, the photon energy is larger than 1.42 eV, then also this photon can get absorbed and this electron can go here, and some thermal energy, some energy will be dissipated in thermal energy. So this process is possible. But if lambda is more than 870 nanometers, the photon energy will be less than 1.42 eV. So if the band gap is 1.42 eV and the photon energy is less than 1.42 eV, that photon cannot take this electron on to this conduction band, and therefore this photon will not be absorbed and will be transmitted through, and this will be transparent. So this is one way of getting an estimated band gap, that you send light on this semiconductor and see at what wavelength it becomes opaque to transparent or transparent to opaque, depending on whether you are increasing lambda or decreasing lambda. So that gives this. So our answer will be that band gap is 1.42 eV. Okay, so let's go to the second question. Now this question says that for silicon, the intrinsic carrier concentration is Ni equal to 10 power 10 per centimeter cube. So in silicon, this Ne, which is equal to Nh when it is intrinsic, so that is equal to 10 to the power 10 per centimeter cube. A p-type semiconductor is made by doping impurity with concentration 10 power 17 per centimeter cube. So in this silicon, which is intrinsic, and then you dope some impurity, and that impurity concentration is given, it is 10 power 17 . Power 17 per centimeter cube. Okay, p-type. This is p-type. A p-type semiconductor is made by this dopant, and with the dopant concentration given this, and the question is what will be the electron concentration. So this is p-type or acceptor impurity which we are doping, and the question is what is the electron concentration. So you remember when we dope a certain impurity, then the other impurity, the concentration goes down because of increased whole electron recombinations, and the product of the concentrations of those two types of charge carriers, that remains same. So if I am doping a p-type impurity, then definitely this NH hole concentration is increased. And how much it becomes? It becomes almost the same as the dopant concentration, because remember, each impurity atom that you are bringing in creates an impurity level. If you have valence band and if you have conduction band and you dope this p-type impurity to make this p-type, then the new energy levels are created near this valence band. These are the impurity levels. Because in that silicon crystal, it comes with one less outer electron, and therefore you have a hole. It bonds with 3 of them, and the 4th one is already broken. Okay, and then electrons can jump from here to these impurity levels, and holes are created here. This becomes ionized. Right, that becomes negative ion there, and then you have holes here. So you have large number of holes here, like that. And since each impurity atom is creating one such level here, the number of levels here or number of quantum states here is same as the number of these dopant per centimeter cube. And remember, when I say quantum state, spin up and spin down, so it will be double of this. Those many quantum states will be created here. But then this ionization is very quick, because this difference is small. This difference is only few tenths of a milli electron volt. And kT itself, K times T itself is at room temperature 26 MeV. So quite often the electrons will fill that gap and holes will be created here. So almost the whole concentration will be same as the concentration of this dopant impurity here. So I can take this NH to be 10 power 17 per centimeter cube, and then Ne times NH, that is independent of doping, and that is Ni square, intrinsic concentration square. This is Ni, this thing is Ni, and therefore this Ne is equal to Ni square divided by NH, and Ni square is this 10 to the power 10 into 10 to the power 10, that is 10 to the power 20 centimeter power minus 6 here, and NH is 10 power 17 and then centimeter minus 1, which is just 1000 per centimeter cube. So these will be the number of electrons which are here. When there was no doping, that number was also 10 power 10. But then because of this doping, this number has gone down to just 1000, whereas this number has gone up to 10 power 17. Okay, the third question. Now the next question says that you have a silicon which is doped with phosphorus. Okay, so silicon doped with phosphorus, and the data given are Nd. What is Nd? 10 power 17 per centimeter cube. This is number of donor ions per centimeter cube, ND, concentration of donor ions. Then the Fermi level is 146 milli electron volts below EC. What is EC? The lowest energy in the conduction band, that we write as EC, and the highest energy in the valence band, that we write EV. So it says that it's a silicon, so you know how much this is. This is around 1.12 EV, and the Fermi energy is 146 MeV below EC. So 146 will be, let's say, somewhere here. This is 0.146, 146 EV. This is Fermi energy. And then another data is given that ED, the donor impurity level, E impurity you can call it, this is 45 MeV below this 45 small m EV below EC. So the impurity level is formed somewhere here. This is 0.146 EV, and then the impurity levels are formed somewhere here. So okay, it's a lot of space problem. So this is EC, and then this is EI, impurity level, and this separation is 45 MeV, so 0.045 EV. So these are the data given. I hope you remember, for intrinsic semiconductor, the Fermi level is in midway between these two, EC and EV, midway between. But if you dope this donor impurity like phosphorus to make it N type, this Fermi energy goes up. So it's not at half, it has gone up. And then when you are putting these impurities, that impurity levels are created, and there are few tens of MeVs I had been talking about. So it is this thing here. The electrons jump from here to here because of thermal energies, and that is how you get electrons in the conduction band. Ne increases, Nh decreases. So this is the data which is available. What is asked? What percentage of donor ions are not ionized? What percentage of donor ions are not ionized? So you remember the mechanism. If I have a donor impurity here, it comes with 5 outer electrons, 4 are bonded, and 1 is still here, which is to start with, which is bound to this donor atom. So it's a neutral atom. It had 5 electrons, there are 5 electrons, and therefore it's a neutral atom. But then this electron, if it goes to the conduction band, if this electron goes to the conduction band, then what is left here is a positive ion. And you say that this donor atom has been ionized. That means the electron has gone into the conduction band. So the impurity level energies are here. These are the impurity level energies. So once the electron goes from this impurity level to the conduction band, your donor atom is ionized. And if it is not, if it is still bound here, then you say that it is not ionized. So the question is, what percentage of the donor ions which are substituted in this lattice crystal are not ionized? Okay, so total number of donor ions per centimeter cube is given here. Out of these, how many are ionized and how many are not ionized, right? Okay, so what we will do, we will calculate the probability of a quantum state being filled here. These impurity levels are created here. So you have created new quantum states, and there are electrons to start with. But then these electrons are going to conduction band, and there is a probability of that. So what is the probability that a quantum state here is filled by the electron, right? So that probability we can calculate, and for that this EF is needed. So probability that a quantum state at energy EI is occupied by an electron. So this probability will be given by that Fermi function f of E, which is 1 divided by 1 plus e power E minus EF and over kT. And since I am looking for probability that a quantum state at energy EI is occupied, so this E here is nothing but this EI, and that one can calculate. So this is 1 over 1 plus E, EI minus EF. So this is EI and this is EF. So what is EI minus EF? EI minus EF will be EI minus EF will be this 0.146 EV and then minus this 0.045 EV, and that will be how much? This much EV, 0.101 EV or 101 millielectron volts. So this is 0.101, and then that divided by K times T. So taking room temperature 300 K, K times T is 0.026 EV. So let us work out how much is this. 0.101. So e to the power, let's work out this much. 1 divided by 1 plus 48.6. So that value is 48.6. So that is 1 divided by 49.6, almost 0.02. But still let me do that. 1 divided by 49.6 equal to, yes, 0.0201 etc. So almost 0.02. So this is the probability. This is the probability of one quantum state being filled here. But how many quantum states are there? The number of quantum states are 2 into 10 to the power 17, right? 2 into 10 to the power 17 because of that spin up and spin down. You have these many donor ions, okay, but then electron with spin up is a different quantum state, electron with spin down is a different quantum state. So total number of quantum states is 2 into 10 power 17 per centimeter cube, and then you have this probability of each quantum state being filled. So multiply that, how many quantum states are occupied? So number of quantum states occupied is 2 into 10 power 17 and then into 0.02, or you can express it this way, this multiplied by 0.04, and that means 4%. 4% of the total donor atoms. So those many electrons are still here in the impurity level, and if the electron is here, that means the donor atom is not ionized, that electron is still here. So the fraction of these donor atoms which are not ionized, that is 4% only. 96% have already ionized. That is this question. Now let me do one more question, and that is on p-n junction. It says that a p-n junction is formed by doping impurities with Na equal to Nd. So you make a p-n junction by doping impurities, and number of acceptor impurity per centimeter cube is same as the number of donor impurity. So if you denote your p-n junction like this, here is the junction, then from one side you have acceptor, another side you have donor, and since Na is equal to Nd, your depletion region will be of equal width on the two sides. So if this is p side and this is n side, this part is same as this part because Na is equal to Nd. The depletion layer width is 1.4 micrometers. Okay, so the depletion layer width is given 1.4 micrometers. So this whole length is 1.4 micrometers. That is given. The potential difference between the n side and the p side, which is the potential barrier. So that potential barrier is 0.6 volts. Okay, you know, when the junction is formed, these electrons will diffuse to this side, they will create negative charges here, and this will create positive charges here. So you will have charge density in the depletion layer, no charge carriers but charge density, and then you have electric field, and you have potential difference, and then the potential of this n side is raised as compared to potential of this p side, and that barrier is 0.6 eV. And the question is, what is the electric field at the junction? What is the electric field at x equal to 0 at the junction? Okay, so if you remember our electric field, this electric field will be in this direction. This is the direction of electric field, positive side to negative side, and therefore it will be negative in the usual diagram. So if E is here, X is here, then you have electric field somewhere here, and then when depletion layer ends, the electric field becomes 0. The electric field is 0 here, and it is linear. And it is linear. Same story on the other side. The electric field is still in the same direction, so it is negative, and here the electric field is 0 beyond the depletion layer. So here it is all 0, and this is also linear, and this is, let us say, E naught, and we need this E naught, or you can call it minus E naught if you so wish. All right, so you can write this electric field, and remember this, let me call this x1. So what equation can I write for the electric field here? This I can write as E equal to, this is minus E naught, and then plus E naught over x1 times x. Just check. This is a linear equation, and then at x equal to 0, E is equal to minus E naught. So E is equal to minus E naught at x equal to 0, and at x equal to x1, this will be 1 x over x1, and so minus E naught plus E naught will be 0, and it is linear. So this is the equation. Now you can integrate to get this v. V will be minus E naught x and plus E naught over 2 times x1 here and x square here, and plus some constant. And you can take v to be 0 at x equal to 0. This is our choice, and that will make c equal to 0. So v is equal to minus E naught x plus E naught x square over 2x1. And what happens here at x equal to x1 and beyond? Okay, electric field is 0, so the potential will be constant. So v at x equal to x1. So this x is equal to x1. So you have E naught x1 by 2, and here minus E naught x1. So it is minus E naught x1 by 2. That's the potential. Right. But if the total potential barrier is 0.6 electron volt, from here to here it is 0.6 electron volt, and it is symmetric here. So if you have 0 potential here and this side it is something, the same will be other side. And this difference from 0 x equal to 0 to x equal to x1 should be 0.3 volts. So this should be equal to this E naught x1 by 2, this potential difference from junction to the end of the barrier, that should be 0.3 volts. And from here you can get what is E naught, 2 into 0.3 volts, okay, and then divided by x1. And how much is x1? x1 is 0.7 micrometers. So that is the electric field. You can write in terms of volt per meter. This is 10 power 6 here, 0.6 here, 0.6 over 0.7, that will be 60 by 7, that is 8.6, something like this, 0.86 in fact, 0.86, okay, let me write 0.86, 0.86, that is this, and then into 10 to the power 6 volts per meter, or 0.86 megavolts per meter. That's the maximum magnitude of electric field which exists at the junction. And then as you go on this side or you go on this side, it linearly decreases to 0. Alright, so we will stop here, and next time we will do some special p-n junction diodes.